Have you ever thought about what happens when you flip a light switch? Mathematically, it can be a real nightmare. The voltage isn't smooth. It jumps from 0 to on in an instant. Now, if you try to model that with your standard differential equations, it gets clumsy. You have to break the problem up into pieces. But there's a much more elegant tool for the job, one that's designed for exactly this kind of thing, the Laplace transform. Today, we're going to see how it turns these messy on and off problems into something as simple as algebra.
So here's our game plan. First, we'll dig into why these on-off functions can break our traditional methods. Then we'll introduce the Laplace method and a super simple three-step strategy to master it. After that, we'll get our hands dirty with two classic examples. And finally, we'll translate all that math back into what's actually happening in the real world. Let's start with the problem itself.
So what is the big deal with a function that isn't continuous? Well, a lot of our go-to methods in differential equations, like the method of undetermined coefficients, they kind of depend on the forcing function being nice and smooth and predictable. The moment it suddenly jumps, our tools just break. And that forces us into a process that's way more of a headache.
Just look at the two approaches here. On the left, that's the old way. It's tedious. You have to solve one equation for when the switch is off, then you solve a totally separate equation for when it's on. And the worst part? You then have to do all this messy algebra to stitch the two solutions together at the boundary. It's clunky. But now look at the right. The Laplace transform method, it treats the entire timeline as one single problem. You get one unified solution from start to finish. No cutting, no pasting, it's just clean. This is exactly why we call Laplace transforms a kind of superpower for these specific kinds of problems. Honestly, they feel like they were practically designed to handle these jumps. Instead of seeing a break in the function as a problem to work around, the Laplace transform just eats it for breakfast and builds it right into the algebraic setup.
And this quote from Material just says it all, doesn't it? This is the core idea, the main takeaway. The ability to look at a system that changes its state, where a force switches on or switches off, and tackle the whole thing without having to chop up the timeline, that is the fundamental advantage we're about to use. So how do we actually do it? Well, it's not magic, even though it feels like it sometimes. It's a system, a process. I'm going to give you a clear three-step roadmap that, believe me, works every single time. Let's break it down. Here it is, our three-step playbook. Step 1, express. First, we rewrite our on-off function using a special tool, the unit step function. This is how we write down a sudden event in a single, clean expression. Step 2, transform and solve. We hit the whole equation with the Laplace transform. This is the magic trick. It turns messy calculus with derivatives into simple algebra. Our goal is just to solve for a variable, y of s. And finally, step 3, invert. We take that algebraic answer and use an inverse transform to bring it back to the real world of time. And a special time-shifting property makes this last step incredibly elegant. All right, theory's great, but let's see how this roadmap actually works in practice. We're going to walk through two classic examples, step by step, to really make sure this process clicks. So for our first case, we've got a simple harmonic oscillator, but with a twist. See that forcing function, u sub pi of t? That means there's no external force, nothing, until time equals pi. And at that exact moment, a constant force of 1 switches on and just stays on. And those initial conditions tell us the system starts out completely still. Okay, step 1 is actually done for us, since the problem is already written with the step function. So we jump right to step 2, transform. We take the Laplace transform of both sides and we get this nice algebraic equation. Now, once we isolate y of s, I want you to notice the structure. We have an exponential term, that e to the minus pi s, and it's multiplied by this other function, h of s. That exponential is the key. It's the mathematical signal for a time delay. It's telling us that the system's main response, which is all wrapped up in h of s, doesn't actually start at time 0. So before we can deal with that time shift, we need to figure out the system's core response. To do that, we find the inverse of just that h of s part. A quick partial fraction decomposition, which is really just an algebraic trick to break a complicated fraction into simpler pieces you'll recognize from your transform table, gives us this function, h of t. Now, this is really important. Think of h of t as the hypothetical response. It's what the oscillator would have done if the force had been switched on from the very beginning at t equals 0.
And now for step 3, we put it all together. The time-shifting property tells us exactly what to do with that exponential we saw earlier. It does two things. First, it becomes the step function, u sub pi of t, which literally keeps the system turned off until t equals pi. Second, it tells us to take that core response, h of t, that we just found, and shift it to the right by pi. So what's the result? The system is completely still until time pi, at which point the response kicks in and starts oscillating as if time just began. Okay, let's try a slightly more interesting case. This time, the forcing function is a pulse. A force turns on at time t equals 1, and then it turns off again at time t equals 2. We can write that down by subtracting two step functions. It's a first-order equation, and again, we're starting from rest. We're going to run the exact same playbook. We transform the equation, and after we isolate y of s, we see something really convenient. We've got two terms here, one for the on event and one for the off event. But check it out, they are both built from the exact same base function, h of s. That's great news. It means we only need to find the inverse of h of s one time, and then we can just apply it to both parts of the solution. So, just like before, we find the inverse of that common h of s. Partial fractions splits it into two simple terms, and their inverse transforms are super easy to look up. We get h of t equals 1 minus e to the minus t. This is the fundamental response of our system to a constant force being turned on. Now we just apply the shifting property to both terms from our y of s equation. The first term gives us u1 of t times h of t minus 1. That's the part that turns the response on at t equals 1. The second term gives us minus u2 of t times h of t minus 2. This introduces an opposite response at t equals 2, which effectively turns the net force off. This is a brilliant illustration of how the final solution is just a superposition, a combination of these two shifted events. Okay, we found the solution, we have the equation, but a bunch of symbols on a page, that isn't really the goal, is it? What story does this equation actually tell us? Let's connect this abstract math back to what's physically happening. So let's really look at this final answer. This isn't just a formula, it's a complete timeline of events. What's the physical story here? Let's trace the story that our solution is telling us. For any time before t equals 1, the system is dead. Y is 0. Nothing's happening. Then, at exactly t equals 1, that first term kicks in. A force switches on, and the system starts to charge up like a capacitor, rising towards a steady state value of 1, but it never quite gets there. Why? Because at t equals 2, the second term activates, introducing an equal and opposite force. The net force becomes 0 again, and the system immediately starts to discharge, decaying back down towards 0. The solution perfectly models this rise and fall. And this, right here, is the real beauty of this method. That one final equation for y of t, it's not just a formula. It's a complete narrative. It contains the before, the during, and the after of that pulse. It tells the entire story of the system's behavior, all wrapped up into a single, compact expression. So, we'll leave you with this question. Now that you have this powerful tool in your toolkit, where do you see these on-off systems in the real world? Think about it. The effect of a medication that wears off after a few hours, or a motor that's programmed to run for a set amount of time, or even a digital signal in an electronic circuit. All of these can be modeled using the elegant method we've just explored. So, what system are you going to analyze first?